Okay, so it's joint work, as you mentioned. So we are going to look at pro-cyclicality effects. And it's a joint work with my former PhD student, Marcel Braütigam, working now at the European Central Bank, and with Michel Lagornia from Primary Solution in Switzerland. So, as said, pointed out by the chief economist of AXA in 2020, he was saying that the major mistake made in 2010 was imposing austerity at the worst moment. And so we will illustrate this phenomenon, which describes well the notion of pro-cyclicality. So what do we mean by this? We know, and it's quite accepted idea, that risk measurements made with popular risk measure as value at risk, expected shortfall, are pro-cyclical, meaning that whenever you're in times of crisis, you will overestimate the future risk while underestimating it in quiet time. So here we can look at an example of financial stock index, so the SP 500. And you see it, so looking at the period of time 2007-2009. So the first year in blue, you compute your value at risk, historical value at risk on 2007 data. So my data of the negative log returns of SP 500. So you see some threshold, some value below 5%. And so this value is the one which will forecast for the next year, the capital requirement for the following year. And whenever you're looking at this, you see that the following year, financial crisis occurred. And in such a case, you will need much more capital to handle it. So now measuring next year, you see indeed that in red, you have a value at risk much higher, and which is supposed to forecast for the following year. And looking at the following year in green, you see that you would need less capital. So somehow you overestimated what the need for the following year. And this makes clear. And as pointed by Gilles Moec, in the worst time, whenever you have to furnish higher capital, because it's whenever things are getting a bit difficult. So having pointed that, it does not mean that there were no, so after financial crisis, of course, a lot of people worked on this issue, especially economists, and in regulatory authorities, you could see that they came up with solutions using a macroeconomic approach, so in the context of Basel III, Solvency II, EMIR. And so looking also at agents approach, while we will tackle this issue in a statistical way. So our approach is complementary, different. And what we wanted was to study empirically and assess mathematically if indeed the way of estimating capital requirements, so with the usual VAR-based risk measure, is a possible source of pro-cyclicality. And we had the following question. So first, okay, we can observe pro-cyclicality, but how to quantify? I mean, you won't do anything if you're not able to quantify this. So it was our first target. And for that, we needed to introduce dynamics in the measurement of risk for this quantification. Then how to explain it? What are the main factors explaining this pro-cyclicality? And how to limit it once you have some tools. So can you work out to suggest some way to limit the extremes effect? I'm going to speak all what I'm going to speak. You can find it out in some references. So that's why I put it. So all of this in the summary, it's just summary, give you an idea. So the first paper is Mathematical Finance in Open Access. So it's explained well all what I'm going to say. We extended that to any estimator of popular risk measure, as I said, to expected shortfall, expected. We have assessed everything theoretically, and right now we are working on this approach for limiting this extreme effect. So first, how to quantify it? So on the left, I think you see it left or right, I don't know, but a proxy for market states. It's as common. We know that a good proxy, the volatility, annualized realized volatility. So we call it VKN, so N being the sample size. So you estimate, if you take, for instance, K equal 2, you recognize immediately your standard deviation, okay? So if now I'm considering K equal 1, I'm with the mean absolute deviation, and it's what I'm going to use mainly. You will see why. And so this square root, it's because it's the annualized realized volatility, so 252 for a year. Now on the right, you have the look forward ratio, what we call it look forward ratio, with the sample quantile process L being the loss. So I'm looking for on 1 year, because it's as asked by regulators, alpha in the threshold, and somehow this at the numerator, it's what I use to forecast for the next year. Okay, so the estimate realized risk a year later, and here of course it's a posteriori, and the denominator is whenever you consider, so it's what people do, using an estimator of your value at risk this year to forecast for the following year. So it's this one Q hat is used as a predictor for 1 year later. So now if, so looking at the realized volatility, so let's look at the plot. So here it's from 87 to 2016. So we see the main crisis, let's say, with internet bubble, financial crisis, the sovereign debt. And so we in red, it's this annual realized volatility. So here estimated with the mean absolute deviation. So you see all this well. And in blue, so in the ratio that I just introduced, of the, so the, let's say what will be in a year divided by my forecast, so how I do estimate this. And you see that, so one, if I made a good job, if I had a good forecast, this ratio should be close to 1. So that's why I just represent the straight line 1. And I have the ratio just oscillating around this value 1. And what we can observe in that, generally, when you have like the low volatility, then the ratio is high, and vice versa. Okay, so somehow they behave in opposite way. Financial crisis as well. So we have a peak for the red, for the realized vol, and the blue is just a peak down. Okay, so using this, it means that it give us a way to quantify pro-cyclicality. And what we can observe is that we have a negative correlation between the realized volatility and the log of the ratio. So here it's negative dependence. If I would have considered just the ratio, I didn't have something linear. That's why we transform. We consider the log ratio, and now the correlation, linear correlation, makes sense. So here, representing on, again, taking SP500 as example, we have on the x-axis the realized volatility estimated with the mean absolute deviation. On the y-axis, we represent the value of the logarithm of the ratio. So as I do have my previous log ratio, log R, in terms of my estimated realized volatility. Okay, and what we can see, I mean, of course, it's not represent everything, but what we observe in this negative trend, slope, descending slope, and the linear correlation, empirical one, correspond to minus 50%. So we, of course, did a lot of experiments using different financial stock indices, and we could always observe the same thing. So whenever we have low volatility, like here, we have a high ratio. So because I'm taking the log, so log of 1 is 0. So whenever I'm using a ratio, it will be compared to 1, log ratio compared to 0. So here, in low volatility, I see that my ratio, high ratio logarithm is higher than 0. So meaning that I will underestimate the risk because the ratio will be larger than 1. So somehow what my forecast will be smaller than what it should be. And in high volatilities, it's reverse. So I can see that I have clearly a low ratio, meaning that I will overestimate the risk. So we can do, and this was suggested by a colleague from Fed, to have some representation to help managers to use this tool. And so here, instead of doing like continuous time, as we have done here, we just do some bins with the volatility. So here, for instance, we consider 10 bins of the volatility. And for each, we are, so now I'm looking, because I don't look at this negative correlation. So here, it's really a way to measure the capital, which was needed. And so again, you see that my reference point is 1, if 1 being what I forecast correspond to what is needed indeed. And so in low volatility, so those low bins, I can compute exactly what is the underestimation of capital. So you see, for instance, in the extremes, the first bin, you see that you have underestimated of 40%, which is quite large. While in high volatility, then you have this overestimation. And so the strip pattern, so it's about 1/3 here that you have estimated. Let me point out also that, of course, for regulators, one side is better than the other. So somehow, I mean, if you overestimated the risk for them, it will be less dramatic. But for the manager point of view, of course, it is a big issue. And that's why I quoted Gilles Morec on this respect. And as risk analyst and manager, and I always repeat that to my students, the goal is not to you need to optimize in both ways. It's very fundamental. So you have to take into account all actors and provide right estimation. So now we have a tool to quantify, so in 2 ways for the manager, as well as a statistical tool with the negative correlation between the log of the ratio and the estimated volatility. And now we want to explain. So what can produce this pro-cyclicality? Is it really because of the use of the risk measure or the way I measure risk? And for that, we needed some models to isolate effects. So we consider first we know that volatility clustering is something quite known. So of course, this we expected to observe this issue of pro-cyclicality because of the volatility clustering and return to the mean of the Kratz model. And indeed, it's what we will see. So we didn't consider a very sophisticated model to estimate the volatility because somehow you would hide effects. We wanted really a direct way to see it. That's why we consider the Kratz 1.1. So that, formulation is just recalled here. And what we wanted to do is to explore if indeed volatility clustering present in data is fast enough to produce pro-cyclicality. So somehow, you need you don't need a year, a period of time too long to be able to look, to see this volatility clustering. And on 1 year, it was fine. So below 1 year, you could see it with no problem. Now, more surprisingly, so the model we used is an IID model. And here, so meaning that you are completely independent of volatility models, whatever you will use to estimate your volatility, hence, of course, independent of business cycle. And so we looked if even with IID, we would observe this dependence between the log ratio and the realized volatility. And for that, as you know, so the tool we are looking at constantly in the log of the look-forward ratio, volatility, and compute the correlation. So here we consider 3 plots. So one being with the data. So again, one example with the SP500. Another one, consider our model gauge to see the volatility clustering. And the third one with IID, so independent of any business cycle. We normalize somehow scaling. You see that it's always named annualized MAD and so on. So to have kind of fair comparison in terms of scaling. And we compute each time. So we represent the log ratio normalized as a function of the volatility. You see that each time you have the slope, negative slope, and the correlation given by on data minus 50%. When using a gauge, it's even emphasized the effect. You see it even clearly with more than 60%. And on IID, you have around 35%. So depending on the tail, we consider Gaussian light tail versus a student to see if the impact of the tail would matter. On the IID, so somehow this was empirically, and now what we wanted is to prove indeed if is it true? Is it only empirical observation? Now can we assess it theoretically? And the answer is yes. So we can really prove those effects. So we consider, just consider this bivariate. So on the first component of this bivariate vector, you have any functional of your empirical quantile, so your value at risk at threshold alpha. Second one, we made it general, but think about, for instance, your MAD, the mean absolute deviation. So here, second component will be any function of dispersion measure, so like to measure your volatility. And you get, under some condition, and here I just point out what I was telling you about the choice of estimation for the volatility. So for instance, if I'm taking the mean absolute deviation, you only need a second moment to be able to prove this, while if you would consider standard deviation, what generally people use in finance, now they started changing that, but still, you need a very strong condition because it's fourth moment. Okay, so I would advise always when estimating to consider the mean absolute deviation rather than the standard deviation. So here we have a Gaussian behavior, and in particular now that I have taken any function of this, I can look at this specific log of the look-forward ratio, and whatever, so of course we have an explicit formula, but here it doesn't matter. You see that you have a positive term on the right in black, and what matters is that you see that whatever you're doing, you will always have this negative correlation. So meaning that even with IID, the way you proceed considering this estimation, you get always a negative correlation. So it was a bit surprising, at least to me. And so now turning to the gauge model, so you have, so now I'm taking in terms of time, of course, And so we have a functional central limit theorem looking at the quantile as function of time, and the same for dispersion measure. So here you get a Gaussian behavior with two-dimensional Brownian motion. And the same, so you're looking at so you have asymptotic normality of this log and the vol. And same thing, you ended up with a negative correlation. Now we extended that to, the question was, okay, is it specific to the value at risk now that regulation turned towards expected shortfall? So our question was, can we prove as well, do we get the same type of results even when turning to expected shortfall or expectile, which is quite used now. There are a bunch of literature on this risk measure, sorry. So I just recalled, so expected shortfall, you know that if L is continuous, you can see it at the expectation of the loss whenever it exceeds some threshold, QLP. You have a different type of estimation, so we try both. Expectile, it's a bit less intuitive in the sense that it's you can get it as a solution of optimization problem. So you have to minimize this and consider the solution in X, which will give you the expectile. But what is nice is that you can show that you have some dejection. So somehow your expectile can be at some other threshold, correspond to some quantile. Okay, so the same for the estimation, meaning that we can use what we have done for the quantile. So actually expectile is almost easier than to deal with in terms of proof than expected shortfall. In both cases, you can also obtain the asymptotic normality of the log of your look-forward ratio with the standard deviation or mean absolute deviation, any estimation of your dispersion of the volatility. And there you deduce as well a negative correlation. So to conclude, we proved the pro-cyclicality of the sample quantile process. So we have done everything dynamically to be able to see what's going on. And we can confirm, okay, it was well known, but never proved. So somehow nor quantified. So we could confirm that it exists, that it can be quantified when looking at it with respect to realized volatility. And indeed, in high volatility period, the way risk measurement done historically on data empirically will overestimate the risk during those periods while underestimating it in low volatility periods. We could identify two factors to explain such pro-cyclicality, which is measured with a negative dependence between realized volatility as a proxy of the market and log SQP ratio. So it has been shown empirically and confirmed theoretically. So of course, as expected, we have the clustering effect of the volatility, and this we can use it through gauge models. But as well, the way risk is measured, so when using IID model, meaning independently of any business cycle. And this is very interesting because it goes beyond any economic study where they look at agent behavior. And so here it also points out the negative impact that the method of estimating risk can have on risk management. We could extend that to any VAR-based risk measure, expected shortfall, expectile. So no matter the choice of the risk measure, it's not because you turn to expected shortfall that you will get rid of this effect. We have always pro-cyclicality. So it's really linked to the way you measure rather than the tool you're using in terms of risk measure. And so now that we have identified those factors, and mainly that we have a tool to quantify this, so it helps us to develop a method now limiting the extreme effects when using historical simulation risk measurements. And I will stop here. Thanks for your attention, and I'm ready for any question.
Yes, thank you. I've got time for another question. In this analysis, you've looked at a stock market index, the S&P 500. How would your conclusions change, or would they change if you looked at other asset classes, like if you use the bond index or an inflation index or commodities, for example?
Yeah, so here indeed, so we looked at many financial stock indices in the study. We consider like 11. Mm-hmm. Now, it's what is interesting for us in the sense that since we look at it statistically and not with agent behavior, we have shown that this the statistical pro-cyclicality is partly due to the Kratz effect. So we have seen when using Kratz, it's even above 50% of negative correlation. So what we know in that it's well known that financial returns present generally clustering of volatility. So somehow, whatever you will consider as financial risk, so you can take bond indices or commodities, whatever, somehow we would see similar effects in all those financial risks because of this clustering of volatility.
Okay, look, thank you very much. We'll have to wrap it up there, but I really appreciate your time, and thank you very much for an informative and insightful presentation.
Thank you.
Thank you.